right, welcome everyone. It's Thursday night, so it's time for another coding challenge. This stream is for entertainment purposes only, and today we're gonna try to crack another coding problem under 40 minutes. Let me just make sure that the stream works. Everything is set. All right, good. So let's start. Is it working, by the way? Let me see. Seems like that. Right, so let's go to the lead code page and see what's the random challenge today. Pick one. Nope, another one. So, all right, it's a medium one. Okay, and seems kind of popular. So let's see if we can crack it under 40 minutes. Given a non-empty array nums containing only positive integers, find if the array can be partitioned into two subsets such that the sum of elements in both subsets is equal. It's interesting. All right. Yeah, it's an interesting problem. Yeah. So the sum is equal. So the sum is equal. Well, just from the top of my head, let me switch to the whiteboard. So the simplest solution, which is n log n, is like this. We first sort the algorithm and have the array from, let's say, this example 1, 5, 5, 11. All right. Then what do? Then we start forming two sets. And basically, we're adding to set 1 from the left and to set 2 from the right, right? So we're kind of moving one element from here and one element from here, and then go to the next one, right? So how do we decide? Let's say we start with set 1, or let's say we start with set 2. We put 11. Then we put to set 1 number. So because we know that on the right side is the largest number than on the left side, we still compare them. If set 1 sum is less, we actually don't need set here. We just need the sums itself, right? Sets is just to represent the things. So if sum 1 is less than sum 2, we keep adding from this side, all right? Once it becomes greater, then we move to this side and keep adding to sum 2 until sum 2 is greater than sum 1, right? Or equal to. So until is less or equal, we keep adding to sum 2. And sum 1, or just less, right? We don't care. And then to sum 1. And then we see if as a result we have two arrays in a way that shows in a way that two sums are equal, right? All right. So this solution requires us to sort things. But I wonder if we do need to sort things. Can we just run linearly and add element to one or another one depending on, yeah, it doesn't necessarily need to sort. Let me give an example where sort doesn't work out. So we have 1, 2, 2, and 3. Let's say it's already sorted, right? So obviously we can, so can we? Yeah, we can combine 1 and 3 and then 2 and 2, right? So it can be splitted, but if we start sorting like this, it doesn't work, right? All right. So how on earth we going to combine these elements? Well, alternative is split it to, so basically we need to come up with just two sets, right? So it's basically can be union thing. So we can, let's say, split it to 4. So we have 1, 2, 2, and 3. And then there should be, okay, it won't work as well. It's still a non-trivial one. So it's not sorting. So this is wrong, right? So let's return back to this example, which is interesting. So if we start with just having two sums, right? We start, let's say, with sum 1. We move 1 here. And then sum 1 becomes greater than sum 2, so we move 2 to sum 2, right? Then this becomes greater, so we move 2 here. The problem, though, once we go to 3, we realize, oh damn, this is 5, this is 3, so they're not equal. But wait a second. If it's only positive integers, right? Isn't it just straightforward? Just take a sum and see if the remainder of division by 2 is 0. Is that straightforward? Let me check. So in this case it works because we sum, it becomes 8 to 0, right? So we say true. Let me give an example where it's here's another good example. We can say 2 and 4, right? So the sum is 6. So equals 0, but it's not. Okay, so this is not that trivial. Right, I see. So but it gives us something, right? It gives us condition when it only can be equal, right? Because if we see all of the examples, right, if there is no %2, there is no upper bound. So we have upper bound on the sum 1, right? Because there should be equal. So the overall sum of them, so the sum of all elements should be, we should be able to divide by 2, right? Nice. And then we need somehow, so the only way to basically verify that is just to find the combination of elements that adds up to this sum, right? So step 1, sorry. Let's start with red. New algorithm, new color. Step 1, sum or yes, we can check %2, then return false, not 0, false, else. We know upper bound now. Okay, we have upper bound, which is sum by 2. Nice. And we know that they're positive. So here is the hint. Because negative, they can reduce the sum, right? So it's not so, but these guys are positives. They are positives. So how on earth? Right. So we are like almost 10 minutes into the problem. So I'm curious. So having this upper bound, right? What it can give us. So the array is non-empty. And obviously, if it's just one element, it's false. So we don't care. All right. If it's less equal 1, if it's equal to 1, because we know that it's empty, nums can be 0 too, but it doesn't matter if there is 0, they won't change anything. From 1 to 100, 100 also doesn't give us anything, basically. The only thing it gives us that the upper bound can be integer, because 200 numbers, even if everything is 100, is what, 20,000, the maximum sum. So it's fine to capture with just regular integer. But then what's the upper bound can give us? So we know the upper bound. So how to combine the elements in a way to achieve this upper bound? We can start with small. It's like an abstract problem, right? You have this size. Then you want to, the only difference, it should be precise. Here we go. All right, I think I know the way how it can work. Let me try. So we need two things. Let's switch to the main screen. So before we start, we just say, okay, two conditions, all right? So if num size equals 1, we return false. Trivial conditions, obviously that one element can be split in two. I don't know, you can just give two. So what's the have just to test this simple condition to do something. Okay, so now if, let's do this int sum equals 0, then we say for const int or we can say out or whatever. Yeah, just int nums and sum plus num. So find the total sum. Step 1. Find total sum. So now if sum %2 not equal 0, return false. Return false. No feasible solution exists. else. And technically, to format this correctly, I need to do this thing. All right. Int upper bound, let's call it UB upper bound, is what? Sum divided by 2. Now, let's also do available elements, right? Which is nums begin and nums end. And here we go, the hardest part. And now we need somehow to use these available elements only to fulfill the upper bound to be exact. All right. We can do random selection from this and then trying to. This is not clear to me personally. Should we just start in the random order? And if it violates, then we subtract and return it to available. And then until we. But then the problem is if you pick one element, then it may affect other elements that you can pick. But ultimately, it doesn't matter because all elements must be picked either in one subset or in another subset, right? So let's see if it's the case. Here we go again. Starting with nums. Now, what do we need to check? If ub minus num equals 0, return true. That's it. No, just kidding. Else if, yeah, should work, 100% should work. Although the way how I start combining it may be the wrong one, right? Maybe very tricky. So let's say I can only combine first one and the last one, and can combine the middle one, right? Returning back to example 1, 2, 2, 3. But then we definitely know No. We don't know this. So we also know total number of elements. I wonder if it can give us something. because number of elements in subsets can be different. Just one can be enough, or two, or three. So we can find the max, right? So if we find the max, let's say 3 in our example, then we subtract it from UB and see. I see. So exactly, if that's straightforward now. If here is the deal, max element. We don't need to find exactly which element should be picked. All we need to check is that the maximum element in the array should be less than this upper bound. So the reason here, I think it's straightforward. I think it's that straightforward, really. Max element equals to max num and max element. And then we should just return max element less or equal to the upper bound. So with the sum, we guarantee two things. Sum guarantees us that, first of all, we can split it by half, total sum, right? Once we split it by half, we already know the total sum of the elements that should be there. Now, if the max element is less than this, there is no way how this upper bound cannot be generated, right? So what I mean is, let's return back to whiteboard. Imagine this case, 1, 5, 5, 5, 11, right? We sum it, it's 22. So the upper bound is 11. We check the max, it's 11, it's done. Now let's return back to the example in like 1, 2, 3, 5. So this is, let's do it 2, 2, 3, 5, right? So it's 4, 7 plus 5, it's 12. So it's 12, which means it's 6, right? Good example. Because in this case, our algorithm will fail. So the max is less. So the max is 5, and max is less than 6. But there is still no way we can find so then the mean as well. So if we know the mean and the max, and the mean is not lower than the max, then the upper bound minus max, maybe this thing. In this case, we don't need even to compare it. Could be. I don't think, at least, why not? So the minimum element we can select also tells us something, right? as well as the maximum. Maximum tell us about feasibility, but then the minimum element tells us about what? Uh, okay, I think it might be the case. So, and then we know that int mean element is what is 101, right? At the beginning, and then we just say mean element is mean of num and mean element. And then we return mean element is less or equal than upper bound minus max. Is it this? So we bounded from the top, then we said, okay, this is max, it should be less than upper bound. And the minimum element should be smaller than the difference between max and upper bound. Is this guarantees it? Or it still makes it in a way that in some cases it passes, in some it's not? It's getting harder and harder to come up with example, because in this case, 2, 2, 3, 5, right? The difference between 6 and 5 is 1, and and the minimum element here is 2, so it's not feasible. But can it be feasible? I mean, can it satisfy this condition and still we won't be able to partition? Let's figure out. I'm tired. So let's just do, oops. Let's switch and see. Mm-hmm. It says false. It's weird. Sum plus num. Sophisticated debugging techniques, UB equals to B. Then what we need, mean element and max element. Looks like it should be there, but maybe not. Maybe not. We'll see. Ah, true. So a return UB equals max element, or mean element is less than UB. Let's see. And now we will figure out what are the cases when it doesn't work. All right, yes, so it's 4, 4, 4, right? There is no way it can be true. So what do we find? So it's 12, so upper bound is 6. Yes, 6 minus 4 is 2, and minimum is 1, and we say, okay, technically can be possible, but it's not. So we can't really tell based on that, based on max or mean elements of the array, um, if it can be done or cannot be done. But what do we know? Let's imagine that our sum always includes the maximum element, because theoretically it should if it's true, if it's possible. It can include any element from the array, because there might be two sets like this. But then it can be just any random number. Really. So so maybe average will tell us something. Ah, no, the average is exactly the upper bound, right? Ah, no, it's a sum divided by all elements. So let me see. In this case, it will be, so the total sum is 12 divided by 4 elements, so the average is 3, right? And what it tells us, it tells nothing. If many people like this problem, it sounds like there is something like simple to get. And once you get it, it's easy to say yes or no. Right, so what can be the simplest way to check there is a set of elements such that we can have sum divided by 2. Obviously, we can just keep summing up, then we have the total sum divided by 2. We know the upper bound for the subset that should be formed, right? Then we might have number of elements, but it doesn't tell us anything. Like in this specific example, let's return back to the whiteboard and see if we can crack this one. So we have roughly 10 minutes left to try to solve it. Otherwise, so by the way, how many passed? Let me see how many tests passed here. It's oh, it's just 5 tests left. So at least we did some something. Nice. Oops. Wrong. Actually, we can just clear it. So all our thoughts are clear now. Let's go with green. Green is a good one. So we have 1, 3, 4, and 4, right? So we know here upper bound or the subset should be 6. And there is no way we can form it. So from the beginning, there is no easy way of telling which one can be combined and which not. Let's say if I start with 1, and let's also give the contrary example right now. 2, 4, and what? And 6, right? So we know that this can be combined with this. Sorry, these two and this one. So we start adding 1, 1, and 1. We got to what? So what are the ways we can find the sum? 1 plus this. So every element in the array is one thing. Then we can check 1 plus something. So there are 4 ways here. Then 3 plus something remaining, right? So it's kind of quadratic complexity in this sense. And then we can combine more and more elements. So it sounds like a union problem to me. So we need to find how to unite these things. But the problem is, if we unite 2, and then later on we figure out it's not the case, Or we can try just pick one element from the subset, subtract it from UB. Yes, I think the first way I thought is correct. Maybe not. If I find something else, subtract it, and then there is no element to fulfill the requirement, what do? I remove back to the initial element and then go with the second element and then third one. So it's kind of like depth first search. Yeah, is it a depth first search? So we go to the next one in the available until we cannot, and then go back and then go another one, no, go another one, no, go another one, no, and then back and back and back and back. Yeah, so it seems like DFS. DFS, let me see. Oh, damn. Default scene. All right, we have like 4 minutes left or something. So we keep this. This is good. Now what do? Now we have an ordered set of int that says available, and its nums begin and nums end. The problem is we can keep iterating like a lot. That's what bothers me. In this case, it's kind of brute force. You go away, no. You go another way, no. Third way, no. Fourth way, no. Fifth way, right? So we can, so let me tell you what the algorithm is. So let's make it private. So bool. Let's just say DFS for the lack of time so we don't spend extra. This thing, what it takes this unordered set available. We make say its reference so we can modify it, whatever. And we can start with some int current. The problem with the set, there may be many. So let's not do set. Let's just do vector. And unordered set available. Let's say not available, but visited. So it will visited indices, right? And it's just this one. So it's nothing basically here. So visited indices. So we can edit it. And then we have also num. And then in current position or whatever, let's call it I, right? Which is basically can be 0. So what do we do is this. Should we also say upper bound into b, into b. So we start with the upper bound. So if ub minus oops, nums I equals what, 0, return true. It's an easy one. The hard one to say else. What do we do if else? Else, if it's else if let's say nums less than 0, right? So it's negative. So we violated. We should return false. And finally, if it's greater than 0, so we might select another element. So we say what? We say visited insert I, right? Then for whatever int j equals 0, j less than length, blah blah blah, j plus plus. So what do we do? I hate it. It will go basically through all potential solutions. See if at least one of them can lead to the next potential, such as the next potential. Oh my gosh. But eventually it will converge. But it's too, but in terms of complexity, it's a nightmare. Visited contains a j, so if contains j continue, then if, yeah, we don't do anything, then if, now it's interesting, dfs of what? Of visited indices nums j and ub minus nums I, all right? So if this is true, so at least once we hit it, we return true. If we hit this and we never encountered anyway, it might be just the fact that in this specific scenario it was false. So we return false. And before we return false, we should visit it. I guess it's remove I, right? So we remove it such that, or should we? No, we shouldn't remove anything because it's just the way we tried it and that's it, right? And because we know that first element always should be included in one such subset, all we need to do is say return DFS visited, which has nothing right yet, nums, we start with 0 position, and now we're upper bound. All right. Should be doable. Oops. Not sure if we passed the complexity test or if it works at all. Of course it doesn't. Yes, pointer. Or if it's a pointer, then I guess we might want to remove it because it's just a single element, right? And we try, oh, possible. Oh, we tried it and it didn't work, so there is no way to try again. Yes, correct. Oh, but maybe we want to try it with a different one. So yes, we might want to try it. Visited, remove I, num size. So it should be find j not equals visited int and right. Yes, not equal. So we have such element. So we shouldn't try it because it's already included. There's no remove. Are you kidding me? Remove element set CPP. Is it set arrays? My set iterator 2, it removes 3. So is it find and then arrays? Oh gosh. So find and arrays, it's not very convenient. No, just say it's erase. Let's try. Right, we're out of time. So let's see if it works at all. I guess it's not gonna pass the time limit. No, this crap. Yeah, it's too hard. Damn, it's like it's just the medium problem, and we failed on the medium problem. But at least we passed all tests but one, right? No, 36. I had a variant that passed it to almost the end. Whatever, 36, 1 out of 160. At least it's the right one. Let's see what I've missed. No, dynamic programming plus memoization. Damn, that's what it is. So it's basically what we did plus memoization, right? 0-1 knapsack approach. Yes, it is. That's why we've got, again, these like values, 200, 10,000. So a target minus a n minus 1, so a target n minus 1. Mem set memoization set size of dp. Time n sum by half. Space n sum by half. At least we got that there should be sum by half. And we passed like there are almost like 5 tests left with this mean, max, average, whatever thing. But I guess the right way is still dynamic programming. So we start with nums. Whatever. Accumulate, find the sum of nums vector. Okay, it's cap by half equal 1, or it's not the size equals 2. If sum is odd, then return false, yes, or only return false, blah, 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 it doesn't matter. Yeah, we got this corner case, it's not interesting. This is the upper bound, right? This is the upper bound, we also got it. So what we missed is the way how using the upper bound we then find the subset. So we used exhaustive depth first search. That's how it's called correctly. And of course it's exponential, but you can solve it using memoization techniques, I guess, or dynamic programming in polynomial time. I would definitely it's not going to be a medium problem, I would say. Because sometimes get this in 40 minutes, not easy. Again, dynamic programming is always like this. If you found the key quickly, then you solve it. If not, then I until the cap. Why? How cap is related to the oh, maybe it's the sum itself. It can be 0 if you don't select anything, and can be whatever it can be. So yeah, I had this idea of finding all possible sums that can be used, and seems like it is the number of all possible sums that we can use is somehow this, and s as a sum by half, whatever. So we start with every element and see how many ways we can add to it, right? I think so. So let's see. Equals 0, obviously. 0 element for I equals 0. Then we start adding element and say I and 0 is 1. Interesting, why? So that any addition is 1. Why? It's interesting. So from I equal 1 to I less than n, and j from 1 less than cap to j plus plus, we do this. J less than nums I. Okay, so the idea is, so this structure helps us to find the combinations of sums that we might have, if I understood correctly. And then we need to access cap, which would be either 0 or 1. And n minus 1 is basically last element because we always reprogram it, because we always compute the next step using the prior one. The non-trivial. I mean, this is trivial. This is trivial. Sum j can be formed using first I elements. If sum j, and it can be any first I elements, but these, why first I elements? So we randomly either select or not select in this sense. All right, whatever. Yep. Another failure. So let's switch back to the whiteboard. So it's 0, space is 0, because we haven't solved it technically. This one, so we got the solution, but obviously it's basically exhaustive search. It's boring. So it's what? It's 36 and 6. Nice, all right. Wasted. Switching back. And where is this thing? Where is my favorite thing? YouTube.
Wasted.
Okay, it's a different one, but also works. Okay.